I want to describe two experiments, two historical experiments today that have been used to find the speed of light to quite varying degrees of accuracy. The first one was performed by Galileo. Galileo's experiment was very, very simple, but on the surface, quite ingenious. Galileo and his assistant stood on two hills a kilometer apart. So Galileo is on hill number 1, his assistant is on hill number 2. They've both got these lanterns that are lit by flames. There's a flame that's glowing inside these lanterns. One on hill number 1, one on hill number 2. They're both covered up. So neither one can see the other person's lamp. Galileo, hill number 1, has a covered up lamp, and his assistant on hill number 2 has a covered up lamp. Galileo has some way of measuring time. I don't know what that device would have looked like. It certainly wouldn't have looked like my watch, or it wouldn't have looked like a typical stopwatch, but he had some way of measuring the time. Okay, whatever that looked like. Maybe he just, 100, 2 100, 3 100, I don't know. Maybe it was Mississippi's, yeah. Don't know. I suspect that method of measuring time wasn't particularly accurate, but nevertheless he had a way to measure time that he felt fairly confident in. So here's how this works. Galileo, standing on hill number 1, uncovers the lantern. He starts the stopwatch at the same time. That light that is now being emanated from this lantern goes towards hill number 2. His assistant on hill number 2 uncovers his lantern whenever he sees the light from hill number 1. That light that's produced by the second lantern now goes back to Galileo. When Galileo sees the light from the second lantern, he stops his stopwatch. So he started it when the first light was produced. He stopped it when he saw the light from the second lantern. Now, his calculation for the speed of light is pretty simple here. He would have just said v, the speed of light, is equal to the distance the light traveled, which was 2 kilometers, right? 1 kilometer there to the second hill, 1 kilometer back to the first hill, divided by the time that it took. Now, I'm not sure what that time would have been, but he would have had a number for that time. He would have gotten a value for the speed of light, which is completely meaningless. Why? What's wrong with this measurement of the speed of light? In theory, it seems to work fine. He's got the distance of 2 kilometers, which is well established. He measured a time that it took the light to go from one hill to the other and back again. And the light travels at a constant speed, so why wouldn't that give us a good value for the speed of light, Parker? Okay, so you've addressed part of it there for sure. When the other guy saw the light from the first hill, he takes off the cover. That involves a fair bit of time, right? A fair bit of reaction time. Okay, well, the speed of light in a vacuum is actually pretty close to the speed of light in air, so that wouldn't be a huge deal here. This is in air, and it's slightly slower in air than it is in a vacuum, but not dramatically. It's pretty close. Parker hit part of it, though. He said that the reaction time of the second guy uncovering the lantern, but there's also the reaction time of Galileo measuring the time. That's the whole problem with this, right? Is human reaction time. Human reaction time is, I don't know, how many of you guys take Biology 30 right now? In Bio 30, I think you do this little experiment where you drop a meter stick and measure your reaction time. Remember that? What was your reaction time? Do you remember what it was? Anybody? Probably like, yeah, it's probably like 0.1, 0.2 seconds. If your reaction time is 0.1 or 0.2 seconds, that time compared to how long it takes the light to go from hill 1 to hill 2 and back again is so massive that any number you get for the time here, any number you get for the time makes no sense. And if the measurement of time makes no sense, then your calculation of speed also makes no sense. Here's, for perspective, how fast light travels. Okay, I can tell you that the speed of light is 3 times 10 to the 8 meters per second, or about 1 billion kilometers per hour. Canada is about 6,000 kilometers wide, from Halifax to Vancouver. If light could travel from a flashlight, let's say in Halifax, all the way to Vancouver, and it couldn't, for various reasons, it couldn't make it that far. But let's say that it could. If light could travel from Halifax to Vancouver and then reflect off of a mirror in Vancouver and come back again to Halifax, and then reflect off of a mirror in Halifax and back again to Vancouver, and so, back and forth, back and forth, back and forth, it would make about 30 of those return trips from Halifax to Vancouver or Vancouver to Halifax and back again. It would make about 30 of those return trips in 1 second. In 1 second, 60 one-way trips across Canada. And that's how fast light travels. Now, Galileo's trying to measure some time that it takes light to travel 2 kilometers. It takes 1 second to make 60 one-way trips across Canada, and he's trying to measure the time that it takes to travel 2 kilometers with some kind of primitive 400-year-old measuring device for time. Like, it's ridiculous to think that he would get anywhere close to a realistic, to an accurate time. And therefore, it's ridiculous to think that he would get anywhere close to an accurate measurement of the speed of light. Here's what I want you to remember from this experiment. Not so much the details, but when you're dealing with a distance that is like that small, in the order of kilometers, human reaction time is going to be so big that any number you get is going to mean nothing. Here's a summary of what we just said in words. So they stood on hills, kilometer apart. Galileo uncovers his lantern, right? Second guy on the second hill, a kilometer away, sees the light, uncovers his lantern. Galileo measures the time with some kind of primitive time measuring device. Calculates the speed of light using v equals d over t. What's the problem with this, though? What is it? Human error, reaction time. The reaction time is so ridiculously high. Even if you think you're really, really quick at measuring, at reaction, even if you think you're really, really quick, even if you are really, really quick compared to most people, you're a hockey goaltender. Your reaction time is lightning fast compared to most people. Your reaction time is still so ridiculously big or large compared to how long it took the light to travel 2 kilometers that there's no way that a human being is going to get a reasonable measurement for the speed of light here. The next experiment that we're going to talk about gives us a much better value for the speed of light. This was performed about 100 years ago by Albert Michelson. It involves, once again, 2 hills. These ones are 35 kilometers away from each other. Mount Wilson, Mount San Antonio, 35 kilometers away from each other. Now, you might think that that makes the difference and that's what gives us a much better value for the speed of light. It doesn't. Okay, 35 kilometers makes the reaction time a bit less significant than 1 kilometer, but not that much. Light still travels that 70-kilometer return trip so ridiculously fast that we would have no hope of measuring that time humanly. Okay, we'd have to use some mechanical device to do that. So here's what Michelson does, and you'll see in a moment why his experiment gives us a much better value for the speed of light, a much more respectable value for the speed of light. You see on 2 hills here, Mount Wilson, Mount San Antonio. Mount Wilson has a light, some kind of source of light, produces flashes or pulses of light. There's also on Mount Wilson an octagon. It's like a stop sign that has 8 sides to it. On each side of this octagon is a mirror. So we're not talking about, it's not like looking at a stop sign and seeing a mirror where you see the word stop. It's like looking at a stop sign and seeing a mirror on each edge of the stop sign. So here's a mirror, mirror 1 we'll call it, mirror 2, mirror 3, mirror 4, mirror 5, and so on. Does that make sense? This mirror has this set of 8 mirrors has the ability or the potential to rotate clockwise, we'll say here. It's not rotating right now, it's stationary right now, but it has the potential to rotate if we so decide. So here's what's going to happen. We're going to take our light source here and produce a pulse of light. This mirror is not rotating. The mirror is stationary right now. This pulse of light will reflect off of side 4, at the same angle that it strikes it. You guys have learned that in Physics 20. It's called the law of reflection. When it strikes it at 30 degrees, it bounces off at 30 degrees. If it strikes it at 47 degrees, it bounces off at 47 degrees. So it's going to strike side 4 or mirror 4, bounce off, strike another mirror on Mount San Antonio 35 kilometers away, bounce off of that at the same angle that it struck, hit side 6 on this 8-sided mirror, bounce off at the same angle that it struck it, and get observed by this all-seeing eye, by whatever the observer is, whatever the detector is on Mount Wilson. So this is the basic setup, although we haven't done anything yet to actually measure the speed of light. Here's what I want to do. I want to start this mirror rotating. I want to start this mirror spinning. So I turn on a switch. The mirror starts spinning, let's say that as it spins, a flash of light coming from this bulb or whatever it is reflects off of side 4. It's spinning, but it happens to strike side 4 at that angle. When it does that, it bounces off side 4, comes down to Mount San Antonio again, bounces off of that mirror on Mount San Antonio, bounces back. But now, remember that during the time it took the light to travel the 35 kilometers from Mount Wilson to Mount San Antonio, and then the 35 kilometers it took to go back again, during that time, this stop sign, or this 8-sided set of mirrors, is rotating. So when it reflected off of side 4, side 6 was in that position. But by the time that it takes the light to go down the 35 kilometers to Mount San Antonio and back again, the mirror has rotated. So side 6 is no longer in that position. Maybe it's like this. If that's the case, then this light doesn't reflect and get observed by the observer. It reflects up here somewhere, and it doesn't get detected. Does that make sense? Like, this doesn't tell you at all yet how we measure the speed of light from this, but does it make sense that right now the observer doesn't see it? It reflects off of side 6 at a different angle because of the rotation of this 8-sided mirror. All right, we want the light to be observed. So what do we got to do? Speed up the mirror. It's not spinning fast enough. Let's put it back to where it was. If we have this little pulse of light reflecting off of side 4 as the mirror spins, reflects off of Mount San Antonio, reflects back like this, and we have a spinning mirror, then we need the mirror not to make that much of a rotation during the time that it took the light to travel 35 kilometers and 35 kilometers back again. We need the mirror to have made exactly 1/8 of a rotation. In other words, we need side 5 to have come in and taken the place of side 6. That way, if during the time that it took the light to travel from here, which was side 4, down to Mount San Antonio and back again, if it's made 1/8 of a rotation, then the light will reflect at the right angle to get once again observed by the observer. So, if we know that the mirror has made 1/8 of a rotation, and we happen to know the frequency of the rotating mirror, and that's a mechanical measurement. Okay, that's a mechanical, this rotating mirror is a mechanical device. We don't have to rely on human reaction time for this. How fast is the mirror spinning? 500 hertz, 600 hertz, 700 hertz. We may be off a little bit on that, but we're not relying on my reaction time. If we know the frequency of the rotating mirror, we can calculate the time that it took the light to travel from what was side 4 to side 5, which came in to replace side 6. So knowing the frequency, we can find that amount of time. And knowing that time and the distance the light traveled, we can calculate the speed of light. Why is this way better than Galileo's experiment? It's not because of the 35 kilometers versus the 1 kilometer. Although that helps, that's not the big reason. What's the big reason? Yep. It eliminates human reaction time. Got it? There's always going to be errors in measurements. There's always going to be uncertainty in measurement. But here, we don't have human reaction time. And that was by far the biggest problem that we had with Galileo's experiment that we've eliminated. Now, when Michelson performed this experiment for the first time about 100 years ago, he measured the speed of light. Remember I told you a little while ago the speed of light is about 1 billion kilometers per hour? He measured it. The first time he measured it to within about 350 kilometers per hour. 1 billion kilometers per hour is the actual speed, and he was off by less than 400. So that's a pretty good measurement for the speed of light. The cost of his device, now keep in mind this was 100 years ago, but the cost of building this device was about $10, which I don't know what that would be in today money, you know, several $100 probably in today dollars. That's still pretty good for coming up with a speed of light that is within 400 kilometers of the actual speed of light. Now, when we see a problem involving the Michelson experiment, it's always going to look more or less the same. There's going to be little tricks to it, unit conversions and so on, different numbers, but the basic method's going to be the same. This is good news for those of you who struggle a little bit with the higher level questions in Physics 30. Sometimes we come across in Physics 30 these questions that are just like, where do I start? These questions all involve the same recipe, much like Physics 20 questions. You don't have to think real hard about them. Here's your numbers. Make sure you watch out for things like unit conversions, and then just do the question, much like we did back in Physics 20. Here's how you do these problems. Step number one, always, step number one, write down two equations. The first equation is V equals D over T, and the second equation is T is equal to 1 over F. V is equal to D over little t, and then big T is equal to 1 over F. Little t, by the way, would stand for the time that it took the light to travel from one hill to the other and back again, which also corresponds to the time for 1/8 of a rotation of a mirror. That is, if it's an 8-sided mirror. If you happen to see a question with a 16-sided mirror, then it would be the time for 1/16 of a rotation. Big T, the period, remember this from Physics 20, the period stands in circular motion for the time for one complete rotation. How long it takes this 8-sided mirror to make one rotation all the way around. And F, of course, stands for frequency in hertz. So write down these two equations every single time, no exceptions. You don't have to think about that, just do it.
So if you have the
Yep.
period of the mirror,
Yep.
and then on that specific one, if you want the period, the
With-
time.
yes, that's exactly it, yeah. Now, step number two, you're going to sub in numbers. Whatever numbers you have. Okay, I don't care what you have given to you, just sub them in. And you're going to get something out of this. What you're going to get out of it is either little t or big T. You're not going to get both. You're going to get one or the other. No matter what givens you have or what you're looking for, the first thing that you solve for will be one T or the other, little t or big T. But here's the thing. Whatever T you get is never the T you want. You want to get the other one. Get the other T. If you solve for little t, you're going to multiply by 8 to get big T. If you solve for big T, you're going to divide by 8 to get little t. Or divide by 16 if it's a 16-sided mirror, right? Assuming it's an 8-sided mirror, it's multiply and divide by 8. If it's some other number of sides, then you multiply or divide by a different number. So think about this. If it takes 2 seconds for 1/8 of a rotation, you would multiply that by 8 to get the time for one complete rotation, 16 seconds. Or if it took 8 seconds for one complete rotation, Then you would divide it by 8 and get 1 second for the time for 1/8 of a rotation. So use these two equations, sub in numbers, get a time, whatever time just happens to fall out of it, and then get the other one by multiplying or divide by 8. And then you're going to sub that into the other equation and solve for what you're looking for. So you might use this equation to solve for little t, and then you're going to multiply by 8 to get big T, and then you're going to go back and plug it into this equation to solve for the frequency. If you used this equation to solve for big T, then you're going to divide by 8 to get little t, and then you're going to take little t and sub it back into this equation to solve for speed. Write down both equations. See which one gets you a t. Get the other t. Sub it back into one of the original equations, the original equation that you didn't use to solve for what you're looking for. Now let's have a look at example number 1 that appears on the example question sheet that I gave you earlier. It says a set of 8 rotating mirrors. Pay attention to that number, right? It's usually 8, but sometimes they give us a number that's different, 12, 16, 24, whatever. Okay, just pay attention to what the number is. Okay, it usually is 8, but not always. It rotates at a frequency of 600 hertz. The rotating mirrors are placed 35 kilometers away from a curved mirror on a second hill. So we've got the light traveling from one hill to the other. Curved mirror, flat mirror, it doesn't really matter. Reflects, comes back. It's 35 kilometers one way. So it goes 35 kilometers down, 35 kilometers back. We want to find the speed of light. What's the first step? Write down 2 formulas. What are they, Mateo? Yeah, V is equal to d over t, and that t is the time for 1/8 of rotation. And the other one is? T1 is equal to 1 over f. Good, 1 over the frequency. So the time for 1 complete rotation is 1 over the frequency. Now, what's the second step? Sorry? Okay, sub in numbers. Sub in whatever you got. I don't know what V is. I do know what D is. D is not 35, it's 70, because it's there and back. And it's not kilometers, it's meters. It's 70,000 meters. But I don't know what T is either, so that wasn't very helpful to me, right? So I move on to the other equation. Time for 1 complete rotation is 1 over the frequency. The frequency is 600 hertz. Look, that gives me a value for big T. Works out to be 0.00166667 seconds. Okay, remember what I said in step 2? You're going to use the equations to solve for one of the T's. But what did I say about that T? It's not the one you want. It's the wrong one. The one you get first is always the wrong one. So let's get the other one. How do you do that, Parker? If I have big T, the time for 1 rotation, how do I get the other one, the time for 1/8 of rotation? Divide by 8. When I do that, I end up getting 2.0833 times 10 to the negative 4 seconds. Now I sub that back into the other equation that I didn't use. End up solving for speed here, and it works out to be 3.36 times 10 to the 8 meters per second. The real speed of light is 3 times 10 to the 8 meters per second. We're off by a bit here, right? About 10%. But that's not bad. Sure is a lot better than what Galileo would have gotten. Once again, because we didn't use human reaction time here. It didn't become a factor like it was in Galileo's experiment. All right, what I'd like you to do now, having gone over an example here, is take a look at worksheet number 14. There's only 3 questions on that worksheet, but we're going to give you the rest of class to finish those up.